Prakash. Okay, sir. 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 122 39 260. Okay, okay, sir. Thank you, sir. Thank you, thanks.
Good morning,
Sir,
everyone. Good morning, everyone. On behalf of VMTW, I, Prasad Gattu, with the support of management and principal, we are organizing webinar on single and two species population model. Let us brief about VMTW, which is an Institute of Engineering for Women, established in 2008. Over last 8 years of existence, it has earned a place among the top 10 colleges in JNTH. The architect behind this Vigyan brand is none other than our beloved chairman, Dr. Laurataya sir, an educationalist. His vision was sustaining evidence of our respectable faculty who proved for securing attractive jobs for most of our outgoing students at undergraduate level. The VMTW is the brainchild of our beloved chairman, Dr. Laurataya sir. He is the person who explored pleasure and satisfaction to work. About our beloved principal, Dr. K. Chandrasekhar Garu, obtained PhD from JNTH Hyderabad and published international journals 38, national international conferences 26, monograph textbooks, book chapters 8, and Dr. T. Srinivasulu is the HOD, Department of Basic Science and Humanities. Now, I request Principal of VMTW, Dr. K. Chandrasekhar Garu, to introduce to today's resource person, Dr. K. Kaladar, Assistant Professor, Department of Mathematics, NIT Warangal, to the participants.
Good morning to, am I audible, sir?
Yes, sir. Yes, sir.
Good morning to all participants. Welcome to the webinar in the subject of mathematics. Before introducing today's resource person, Dr. K. Kaladhar, Assistant Professor, Department of Mathematics, NIT Warangal, I would like to say a few words about our college. We are offering BTech, ECE, CSC, IT branches and PG specializations in the ECE and CSC departments. So we have NBA accreditation. 90% of our students getting placement in their final year. Coming to our today's resource person, I'm very thankful to Dr. Kaladhar. So Dr. Kaladhar K, Assistant Professor, NIT Warangal, he did his MSc Applied Mathematics and PhD from NIT Warangal. He has published 40 papers in internationally reputed SCA and Scopus journals and many papers in conference proceedings. So presently he is guiding 2-3 students. One student has already completed his PhD. 2 students are under progress. And he worked as assistant professor in mathematics department in NIT Puducherry for 6.5 years. So besides academic work, he also worked as a chief warden in NIT Puducherry. In spite of his busy schedule in NIT Warangal, he is busy with workshops and FDP programs. He accepted our request to deliver today's talk. And to his credit, he also received Professor Meenakshi Sundaram Memorial Award, Best Paper Award in the year 2011. Thank you, sir. So thank you for accepting our invitation as a resource person for today's webinar. Now I hand over the session to Dr. K. Kaladhar, NIT Warangal. Kaladhar, sir, I'm handing session to you.
Yes, sir. Thank you. Is the problem
Please,
with my internet or your internet? Yeah.
Your voice is audible, sir.
Yes. I'm sharing the file.
Okay, sir.
Yeah. Is it visible, sir?
Not yet, sir.
Sir, is my slide visible?
No, sir, not
Hello?
yet came this. No, sir.
No. But already I shared it. Now, sir?
No. I'll ask our. Yes, sir. Now it's okay, sir. You
No, it's
maximize
okay.
it, sir. Sir.
Yeah,
Okay,
I'll do it. I'll do it. Yeah. Now, sir? Is it all right?
It's okay, sir. Now all right, sir.
I'll proceed.
Okay, sir. Please proceed, sir. Please slideshow, sir. Slideshow.
Yeah, it is.
Right, sir. Now it's okay. Fine. Very good, sir. Fine, sir.
Yeah, fine.
Right.
Yeah.
Okay, sir.
Good morning, all. First, I would like to thank my friend Dr. K. Chandrasekhar. So, thank you, sir, for inviting me to give deliver this topic. Yes. Good morning to all. Myself, this is Dr. Kaladhar from the Department of Mathematics, NIT Warangal. Actually, for the past 6 to 7 months, we are listening only one major news, that is COVID-19. Everybody is talking about it. Actually, what is that? So, in the this short 6 months or 7 months time, our researchers published more than 30,000 papers only exclusively on this COVID-19. Among 30 to 40% papers are related to the medical kind, that is drugs, various drugs they are applying to this and they are giving a result. Those papers published. The rest part, about 60 to 70% papers were published about these COVID species, right? How it is spreading, what is its spread rate, and regional level, national level, country level, and of course in the entire globe level. So around, just imagine, around 20,000 papers got published in the short span of 6 months. All are well reputed journals with ACA indexed journals. So I thought that no, this is the of course opportunity to express few things about such kind of modeling problems and single and two species models. So I've taken this problem and brief about what is actually mathematical modeling, and I will give you sample examples. Sample approach which was known to us, right, and which was delivered to the VTech students, our engineering college students, and the rest how we are extending that concept. That approach I will give you, but much details I cannot give because of this research restrictions. I cannot share. But the thing is, basic idea how we are processing it in modeling and how we are delivering to the common people like through journals, that I will share. So actually, first what we are doing with being a mathematician, why we are taking mathematical modeling in biology actually, right? So this is a species all related to the biology. There are two things. Frequently I'll use the term called population. This population may be meant for these bacteria, tumors, or else people present. So in two ways we can take it, and at the entry level we'll be taking these things with in terms of this public population. Then we'll apply this to the tumors and these species and all. Okay, yes. And no in mathematical modeling, no, how will spell that mathematics? Actually, this mathematics is consisting of the study and the developments of the methods. Here this mathematics will have only methods and their results. If with the help of those methods, know how to solve a particular problem, those things will be there in the mathematics. But the aim of biology is different, right? Here in a natural world, right, what is the phenomena of the tissues and all, those things will be there in the biology, right? And those descriptions and explanations, yes, will be there in the biology. Now here in modeling, no, with the help of mathematics, we are using this mathematics as a tool to explain and to make the predictions of this natural phenomena, right? To give about to give the nature of those uh, structures, biological phenomena, we are taking mathematics as a tool. So here mathematical biology, which involves mathematically modeling the biological phenomena. Here biological phenomena we are taking and we are giving mathematical model for it. And here how we are using these models, right? First we may have precise ideas, right? We'll be having ideas in our mind. So with the help of implicit assumptions, some assumptions will be there. With the help of assumptions, yes, we are taking the models. This mathematics, concise language only that encourages clarity of communication. Now here, suppose if you want to express something like COVID is spreading just like that, okay, that is a general statement. But instead of that, if you are using mathematics, right, 2% of population getting affected, 5% of the population getting affected, this result analysis with this, if you are giving it, right, it will give more clarity what we are giving it. So in that way we are using our mathematics. Actually, these mathematical theorems and the computational resources, we are accessing it in modeling and as well as to express the things in here. And one more thing is there that we can safely test the hypothesis, right? Here this is not a risky one, right? When we are, suppose you might have heard that our COVID this vaccination is at third level or second level or fourth level. Why we are doing so? Why we are not applying to the human, right? Here we feel that no, humans of course is a special, right? We cannot apply just like that. So instead of that, what we are doing, what they are doing, if we are going for the test, especially of course we'll try these drugs vaccinations on animals who cannot speak actually, right? So we'll apply on them, right? And if result is fruitful, then we'll take a special permissions and from the patient also, right? Not only from authorities, we'll take the permission from the patients also. Then only we'll go for that testing, right? We'll inject the vaccination. But the thing is here, in mathematical modeling, that advantage is there. Before going to going for experimentation, here in the lab itself, we are doing it and we are getting conclusion about it. And if the conclusion is proper, right? And it's look like valid, then only we'll go for the experimentation. And who are having background of statistical analysis, they could get it about this testing of hypothesis, right? And we can predict the system performance under the tested untested conditions. Okay, and the system performance also we can test it with the help of this mathematical modeling. But the thing is, here the mathematical modeling also has limitations, right? If you take no easy math, if you want easy mathematics, right, then the problem may be unrealistic. I means what? It may not be closer to the actual situation, right? It may not be closer to the actual the problem, right? And in other way, if you want more realistic model, and in that case, what we have to do, we have to consider so many constraints, so this, that, this, that. So each constraint will be injecting with help of a parameters. Our problem will be consisting of more parameters, then the problem will be complicated. And complicated is all right, but the thing is, when we are going for it's a solution, we have to be more cautious. Otherwise, the result may take in other way that leads to the another problems, right? I mean to say that critical problems also we can, but the thing is we should be more cautious. Okay, and sometimes no, yes, unrealistic conclusions may be possible with the help of mathematical modeling. That is the reason why we'll use to try with this mathematical modeling in various ways. Okay. Yes. Now this is a modeling process actually. Now here we'll be having these real world problems. Yeah, we'll be having real world problems now. So real world problems, for them we are taking some assumptions, right? With the some assumptions, we'll be taking model world problem, right? And I'll explain what is this model world problem. So after taking this model world problem, we are formulating it and we are converting into mathematical model. Mathematical model consists of simple equations. With the help of our knowledge of a mathematical analysis, we'll try for their solutions and we'll be getting numerics. The numbers, whatever we are expecting, will be getting. So these model results will analyze to the model world, then will interpret the results, will validate the results to that entire real world. That is what happening in that entire process. Here we are going from here, and finally we are reaching it to the real world. Right, and unnecessarily, one precaution is we are taking it, right? We should not take things get multiplied, this and that, without a proper reason, right? If reason is there, we have to add it. Yes, and here the model world problems will consist of many things. Okay, and the thing is, when we are going for the analysis, what we'll do is we'll neglect some effects, okay, and who are not required to study. And things that affect the model, but whose behavior model is not designed to study, right? Okay, some effects may be there, those may be affecting your system, but thing is, since you are not studying, we are neglecting them. And here we'll be taking things the model is designed to study, right? Whatever the things we require it, and we are incorporating in that. Okay, and the thing is, this is like a special case of your original problem under special considerations, right? Like yes, when you are studying about the COVID virus, right, this coronavirus, yes, we'll be talking about your domicile also, right? The nature of this may be different from place to place, country to country, region to region. Okay, so such considerations we have incorporated. Yes. And the first thing is, there are 5 stages in modeling. First, we have to ask the question what we want, not what you or what me, what we want. First, we have to take that. Then, what kind of approach is required? What kind of modeling is required for your requirement? That we have to take. Then we have to formulate it. After formulation, yes, we have to go for the solution of it. Then we have to validate it, if possible. Of course, many times we are looking for the validation because yes, we are dealing with major issues like tissues, and we have to answer the questions whatever we raised from the earlier one. That's what we have to take it. Yes. Now let us take the actual content, right? That is about mathematical modeling. And in this species history and story, what are the things we'll get it and how we are modeling? Will let us see now. Now, the major, of course, our topic consists of species. This species I already given an introduction. This is a living organism like your coronavirus, sorry, our coronavirus. Yes. Now, it is the virus particles will be having a similar nature, and who are capable of exchanging genes from one virus to the another. Okay, it is generating, and and the main reason, main thing is interbreeding. Okay, they will grow internally. Such kind of objects are called species, right? The best example, of course, your corona species. Next one is cancer tumor. You might have seen in various places that how cancer got spreading over. Initially, inside the body, at a small place, it will be located with one or two tissues, right? Those tissues sometimes may be killed by our soldiers' white cells. Then there won't be any effect to our body. But the thing is, if those got defeated, then it will be spreading to the entire body. Just explosion will be there, so it will spread over to that entire body. That you could see somewhere, right? And maybe in the news or media, whatever it is. The next word is prey and predator, right? Many mathematical modelings consist of prey and predator models, right? What is prey and what is predator, right? I'll give you one simple example here.
Earphones,
Yes.
beta.
Yeah. Now here, I'm giving example of animals. Sir, can you listen? I'm audible. Prasad sir.
VMTW under?
Yes, sir.
Yeah. Okay.
Yes, sir.
Now here, yeah. Now here, if you take simple example of lion, right? It, for food, it is depending on the other animals, right? Right? Various animals. Right? It will take almost all the animals, right? So here, for food, for animal that naturally preys on the others. So there is a predator, and who are suffering, right? Who got killed for some others' food, those are called prey. So, of course, one common
Kaladar, sir. Not audible, sir.
not audible.
Yes, sir. Now, yes, sir.
Yes. One of the simplest experiments in biology is tracking cell divisions, right? How cells got explored. That is the simplest example, right? And in analytics dynamics, but tumor cells divisions, another example. Just you see how the tissues got spreading over. Yes, those will spread like. Equation only which involves the function and its derivative. A derivative is a function representing the change of dependent variable with respect to an independent variable. Especially in biomathematics, we'll be taking that independent variable as a time. Right. Now we'll go for the modeling, and of course, which was explained to our students, but in some other way I will take it. Right. Okay. So suppose if n is representing the bacteria's density, that is nothing but the number of bacteria present at any time. This is, we are taking it as a continuous function. As time increases, the number varies, changes in either way. Maybe sometimes increases, sometimes it decreases, right? Then the derivative of n with respect to t is also another function. That is, we are taking it as a dn by dt. So in the limiting process, the dn by dt will be taking it as a limit delta t tends to 0 and of t plus delta t minus t. This is a simple definition of a differentiation. That's what we are taking it. So then here we are taking n of t as a bacteria as a density, right? Then here we are assuming that reproduction rate of those bacteria, I'm taking it as a k.
But your voice is not audible.
Just a second, sir. Yeah, now, sir.
Now, yes, sir. Audible, sir.
Yeah. Yeah. Visible? Yes. This, yeah. Now we are taking number of bacteria, getting some disturbance from somewhere else.
Sir, sir,
Of number of bacteria after some time will be getting how we are getting. This is initial number of bacteria at time t. This is net change over this reading time. No, yes, we have to be very careful. K times of n of t. This is k times of n of t. This is n is a number of tissues or number of bacteria at time t. So this is the increasing net change with respect to time. So after rewriting it, what will take? I'm taking this n of t into LHS side, n of t plus delta t minus n of t by this delta dt I'm taking into LHS side. This is k times n of t. So here,
Kalada, sir. Excuse me, sir. Excuse me, sir. Excuse me, sir. Kalada, sir. Your screen not sharing, sir.
no. Now, sir.
Now it's correct.
Yes, sir. Yes, sir.
Okay.
Now, okay, sir.
Yes, yes. Okay. Yeah. Now here, we got from last slide. Yes, when we are taking dt tends to 0, that is a simple differential equation. The differentiation dn by dt, we are getting it as a kn. So this is a simple differential equation we are getting. Now in earlier studies, no, we used to take this expression directly, that the rate of change in the population is directly proportional to the population present. So this k, we are taking it as a proportionality constant k, right? And this k may be positive or negative, depends on the bacteria. So this problem is called exponential growth problem if k is positive, which was given by Malthus in 1798. So this is a simple equation. We can get analytic solution. It is n naught into e power kt, where the boundary condition n naught
Sir, audio.
Excuse me, sir.
Not audible, sir. Kaladar, sir. Please unmute it.
Excuse me, sir. Kalada, sir. Your voice not audible, sir. Please unmute, sir.
Yeah. Sir, now?
Now okay, sir. Now it's okay, sir.
Now it's okay, sir. You can proceed,
Hello.
Kaladar, sir.
Yes, sir.
Yes, now it's okay. You can proceed, sir.
Yeah. Now is it visible, sir?
Yes, sir.
Visible, sir. It is also visible, sir.
Yes. No, maybe network problem. Okay. Yes. Now here in biological way, this mathematical biology way, yes, we are taking the terms in different way. Can you hear me, sir, now?
Yes, sir. Yes, sir.
Yes.
Now
Now
it's very
here
clear.
we are taking, yes. Now here we are taking the term, instead of taking just simply population net change dn by dt, we are taking another way, that is per capita growth. So here the net change per individual, that we are taking it, the net change in particular region, so that we are incorporating. So the rate of change by the population we are taking. So this actually growth or no maybe decrease, the net change maybe depending on various factors. Now, if you take the population of a particular city, that may be depending on many ways, but here we are considering number of births and deaths. We are assuming it. Apart from that, no migrants also will be there. Suppose in a city, number of births we are taking it as a B, and number of deaths we are taking D. And some migrants who are looking for a job, of course, they may enter into the city. So with that, the population may increase with this city, and the other city, of course, population may decrease it. That we are not considering about other, we are considering here. So that factor, of course, that additions and subtractions, if it is, we can add it to B, and subtractions like deaths and who are leaving the city, we can add into D. So that net change we are taking it as R. So per capita growth rate is R. Per capita growth rate is R. I'm repeating it, right? So actually this model is similar to same as that earlier model, but the way how we are expressing it is different. Now if you take this n into the RHS side, dn by dt is Rn only. That's what we got it earlier, right? And the solution is n naught into e power rt. So this is exponential model only. You see the solution is depending on exponential curve. Here this R is net change, right? So that may be growth or decay. In general, when we are talking about the population and the tissues, bacteria, growth is noticed it. Here, if you see it, that is exponential curve here. When R is positive, as time increases, this population goes like this, extending like anything. And when if R is less, then it is decreasing and decreasing like this. But the thing is this concept realistic? Realistic means which we apply to the exact situation, what is happening or what we are facing it. That is not. Why so? Because the thing is, this is exponential, growing up to what level? Will it grow just like that up to infinite level? Certainly not. So that point has to be incorporated here. So that is the reason why we are taking exponential model. Is not that realistic, right? It is realistic until under certain conditions. I already started in mathematical modeling. We are taking and a limited time domain. Maybe yes, we are taking it into when it is going to be double that level. When we when we 3 hours and a limited time domain, this is all right. But the thing is, if you want to continue as a continuous function exposure, then this model is not that realistic. So why so? I'll give you one simple example. Let us take our Hyderabad city, right? And no, it having capability of giving 10 lakh jobs or 5 lakh jobs, 10 lakh jobs. Let us take 10 lakh jobs. Then what will happen here? Who are looking for the jobs? Those will try to enter into the Hyderabad city, and those will try for that job, right? And up to what level those will enter into the city? The first thing is, yes, no, now how many jobs are there? Till filling those vacancies, people will use to come to the city. After that, they will not, right? And of course, some people may leave and some people may enter. That is continuous process. But the thing is, the system that will be ending with one particular certain value. That is, of course, capacity, right? The job source in either of the city, right? That is limited. And I'll give you another example. Suppose yes, food production is there in that particular city or else in one particular place, right? A number of persons are there to eat it, right? How much food is there? If food is more, right, food is like excess food is there and the people are very less, then those will live comfortably and those will enjoy the food for long time, certainly long. But thing is, if a population increases, right, increases just like that increases, then up to what level the population increase can be noticed it, right, until the food lasts, right? For to how many people we can supply the food. So based on that only, right, we can expect the population of their survival. After that, no, yes, you might have seen in various countries, right? We were, of course, a few African countries are there. Those people are dying because of the shortage of food, right? So the situation is like, I mean to say, for every growth, certain threshold is required.
Hello, sir.
Excuse me, sir. Kalada sir. So your voice is not audible.
Yeah. Yes. Yes. No. Okay.
Okay.
Yeah.
Okay.
Now, things we have to consider. So ultimately, directly speaking, the population is directly depending on the resources available in our system, right? So how many resources are there to survive the population? So until that time, this population growth will be there. So that's what we have to add into that exponential model to become more realistic, right? So that's what we are taking it. This reproductive rate, that the population growth rate, is directly proportional to the nutrient concentration, that is the resources available here. So R is directly proportional to C. So here we are taking K as a proportionality constant. Here the net change in the resources, right? Suppose there are 10 units of bread and 1 unit got consumed. So with that, no, yes, one tissue got generated, right, improved. So here what I mean to say, if population increases, then these resources will come down, the net change in the resources will reduce it. If the population is reducing, then the resources will increase it. So that is a dc by dt. So after solving it, we are getting C as a C naught minus alpha n. This is C naught is the initial resource, that constant value we are taking it, and this is C we are replacing back to this R. So R is K times C naught minus alpha n we are getting. So this R value we are substituting in our exponential model. Dn by dt is n into it was R. So in place of R, we are taking it as K into C naught minus alpha n. So after rewriting it, okay, yes, dn by dt is K C naught n minus 1 minus alpha by C naught. We are taking it, right? And for our convenience, here K is a constant, C is not is a constant. We'll make another new constant, right? We'll be taking a new constant it as a lambda, and this alpha by C naught we are taking it as a K. So this K speaks about the carrying capacity of the system. So carrying capacity means the system up to what level it can bear the load. That no, we are in terms of population also it will give the same meaning. So that model is so called logistic growth model. That was simple growth model, and this is logistic. With logically, yes, we are incorporating it. So, and this is also called as extension of exponential population growth model, right? So in other way also we can represent it in terms of per capita growth, that is 1 by n into dn by dt is lambda into 1 minus n by k, right? Here per capita growth, this how we are interpreting here, this is depending on the carrying capacity k, right? If n is more, population is more than k, so what will happen? This is more than 1, than 1 minus more than 1 is negative. So we can expect population reduction, growth reduction will be there, that is negative, we are getting it. And if this population, initial population, is lesser than that of carrying capacity, then this value is less than 1, 1 minus less than 1, like 0.5, 0.6, 0.9, then it is positive, then we will notice the growth, right? So that's what I've taken, right? Here in this population logistic model, this term is called intra-species competition term. What happened here? So whenever population is reaching the peaks beyond the control, so in such cases, this interspecies competition, right? Because of that, here some people are living out. So this is called intra-species competition term we are getting, and this is balancing our system. I'll give you another example, which will continue the earlier example that I already told, that Hyderabad is having capability of 10,000 jobs, right? And some talented people got in. So in such case, ultimately, companies will look for the talented. In such case, some people who are not updating their knowledge, who are not working sincerely, may lose their jobs. So those have to go out, right? So the final thing is the system is to be balanced. Yes. Now you just see it, right? This is that logistic solution is N of T is this one, and this is some solution procedure is very simple. It's very separable type only. This N into this entire thing is a function of N, and we are taking into LHS side, and we are going for partial fractions, and we'll get the solution. I'm not going for that solution, right? So this is the solution here. So what will happen here when we are taking this curve, right? Graphical representation of this, right? When the t is 0, initial stage, so e power 0 is 1. So this 1 and 1 will go out, k and k will go out, n naught will get it. So initially we are at population n naught. That's what, of course, we are considering it. As a t takes infinite in the sense we are taking a large time, right? Okay, so when t takes infinite, this is going to be 0. This entire expression is going to be 0, and end of t is taking a k. What does it indicates? Right, when t is maximum 1, our population is not going just like that, it is controlling, and it is coming down to the k value. This k is a carrying capacity here. So n naught may be anywhere, right? No, initially that initial population may be less than k or greater than k. I already told you that when n is less than k, there is an increase, growth increase, but the increasing is not abnormal, right? Up to certain stage, until reaches the threshold level, this carrying capacity level, population will increase it. After that, it will stabilize it. Now here it is, if it is more than k, it is decreasing and it will come out. So this speaks about the logistic curve. Yes. Now, after taking that, we have to one more important factor is that we have to take about their stability theory, right? We have to under what conditions our system is going to be stable, and it will speak. So for that, we are going to take x naught as f of x, then x naught is a fixed point where x naught is a solution of this f of x is equal to 0. This is a linear stability theory. A complete picture has been given, but I'm not going for that complete explanation of that stability theory. I'm giving just outlines of that. So we are getting the points, roots of this f of x is equal to 0. These are equilibrium points, are the fixed points. So those at those points, we can say that with the help of those points, we can say that how our system is, when it is stable, when it is unstable, right? And in general, these fixed points we will denote it by with x stars, right? We are taking points for x, so we'll be denoting with x star 1, x star 2, x star 3. Likewise, we'll denote, right? And after getting the points, now we have to look for the points whether those are stable points, right? Or else unstable points. A stable point in the sense, if we are moving a little away from one particular point, whether we'll come back or not. You see, we have from the city, other company will catch you, right? So that is called stable, right? Otherwise, no, that point we have to say it as unstable. But to say about this stability, the concept is very simple. We have to take the first derivative of this f, and with at fixed points, you just test its nature. If it is less than 0, that point is called stable point. If it is greater than 0, that point is called unstable point. You see here in this graph, we are net for net change. I am giving graph here, and here, yes, the points.
What is a fixed point?
A fixed point where we can get stability about it, sir. That will be getting with the help of a derivative.
How to get the fixed point?
Taking these f of x, roots of this f of x will be getting it. Okay.
Means what? We have to equate f of x to 0?
Yes, we have to get the roots of that.
Okay.
Okay. And here I gave one sample points 0, n1, n2, n3, and n, right? And if it is a stable point, here you look at it, these species that we are approaching to n1 only, because this is a stable point. Here, even it is population is more than n1, it is trying to come to n1 only because it is stable. Since n2 is unstable, you see the species who are moving towards n1 and who are moving towards n3 and who are moving towards the stable point. So that's what stability says, right? And of course, my focus is on modeling only. The stability analysis is different, is ocean, and I'm not touching those complete details. Outlines I'm explaining here. Now, for this our logistic model, yes, so the fixed points here, this is f of n lambda n into 1 minus n by k. So we are taking zeros of this. So zeros of this is n is equal to 0 and n is equal to k. Two fixed points we are getting, those are equilibrium points, right? And to say about stability, yes, we are going with the double derivative, and this double derivative is lambda into lambda minus 2 lambda by k into n. So here, when we are taking first equilibrium point 0, this is going to be 0 lambda. We are taking it is lambda is a constant, a positive constant we assumed earlier. So this is lambda. We are getting this is positive, and this 0 point is a unstable point, and the k is stable point, because we are getting f dash is minus lambda. Lambda is positive into minus is minus lambda. It is a negative. So n2 point, this is k, is a stable point. And of course, in our logistic curve also, you could see that, okay, how the population value, species values are going it. As the time increases, those all are converging, all are stabilizing with respect to the position of n naught. It is settling at the value of k only. So k, that point, of course, is called a stable point. And if you see that exponential versus logistic, this graph, of course, I've taken it from some other study, right? These values are, don't think about these values. Here, this is exponential, it is right, increasing, but the logistic one, it is settling at the carrying capacity value. Now here, if you see this,
is there any phase portrait is there with you to give the stability, instability, conditional stability?
No. I'm not talking about the stability part. Just I'm giving the outlines. What are the things we are getting in my modeling, right?
Yeah, in your presentation, lambda greater than 0 unstable, you said.
Yes.
And minus lambda less than 0 stable, you said. Both are the same.
Yes. No.
Both
one is negative, right? Minus lambda is negative, right?
Yeah, negative.
Lambda is positive, minus into minus is there, no?
Okay.
Because of that, it is negative. Okay, lambda is positive, but we are getting f dash value as minus lambda.
Okay.
Now here, dimensional analysis also is important part, because the thing is, since it is a simple population, we come across only two parameters. One is lambda and k. But when we are going for the higher order equations and coupled equations, we'll be getting more parameters. In such case, our system may become complex. So in such case, we are looking for the non-dimensional analysis, right? So here I'm considering n as a px and t is a mu into t dash. So with that, this our logistic equation is becoming dx by dt into x is x into 1 minus x, and the other parameters I'm choosing as 1 by lambda and p as k. So if you see this equation dx by dt is x into 1 minus x. So in this, there is no other parameter which is involved. In such case, comfortably we can process it for our solutions. But yes, interpretation why that case we can incorporate the parameters and we can give it to the real world problem, real world, right? That's what. So the advantage is there with the help of non-dimensional analysis. Now, but the thing is still it has certain limitations. What is that? This per capita growth rate is lambda into 1 minus n by k. Yes, when n is 0, when initial population, let us assume that we are at 0 or low level. So in this case, what happens here? N is 0. This entire value n by k is 0. So lambda we are getting it. So when n is 0, per capita growth is lambda. Lambda is a positive. And when n approaches to k, so k by k is 1, so 1 minus 1 is 0. So this per capita growth, it is approaching to 0. So what happened here? If you see this, when we have a minimum number of tissues, and if it is 0, growth rate is maximum. When we have more tissues, k, then the growth rate is 0. So this is somewhat not accurate, right? Because the thing is, you just imagine when we have one or two, the growth rate is maximum, and when we have use, the growth rate is minimum, right? Like almost 0. So this problem was identified by Professor Ali, right? So he thought that okay, we have to extend it to certain level that this problem has to be overcome. So for that, no, he added another, that is he added another term, that is n by k naught minus 1, which is no, with certain restrictions, no, yes, which has to be more fit to the realistic model. So that n by k naught and minus k, he introduced another parameter, so that is k naught, which is in between 0 and k. K is a threshold and 0 is a minimum. So with that, if you see 1 by n into dn by dt, right, in between n value, we are taking it from k naught to n, right? So that we are getting it as a parabola we are getting. So with this parabola, Professor Sergei Petrovsky recently, right, in 2013 or 14, I guess, right, he explained the concept that there is an intermediate threshold, right? Whenever the population logistic models are there, right, even there may be a growth, but after certain point, there will be decay will happen it. So this was explained by this Professor Sergei Petrovsky. Yes. Now for this same story, yes, we are taking dimensionless analysis, non-dimensionalization, we are taking it. So after that, I'm not going for those non-dimensionalization details. So finally, we are getting this logistic model with Ali effect. So this Ali effect, we are getting it as x into 1 minus x into x minus, we are getting. So the same approach we have to take it, equilibrium points we are getting by taking zeros of this equation. So x is 0 will get it, x is 1 will get it, x is beta will get it, and the beta value will be in between 0 and 1. So that's why I have written beta in the middle. So they are getting 3 equilibrium points. Then we'll be going for there about the stability. So here in the stability, f dash value, of course, I derived it here, and at each and every equilibrium point, I tested it at the nature of f dash. So when x is 0, it is minus beta. When x is beta, this is beta into 1 minus beta. In general, beta is in between 0 and 1. So this is positive only. So this entire expression is positive. And this f dash at x3 point, it is getting it as minus into 1 minus beta. 1 minus beta value is negative, but sorry, positive into minus is that this is negative. So overall, if you speak, if you look at these x1 and as well as x3 are stable points, x2 is unstable point, right? So that curve here is beta, right? When the population is inside, it is trying to come down to this 0. If it is after beta, it is going towards 1. So this is what we noticed it. And after that, this research was not stopped with this Ali. Ali also not given. This is called Ali's strong effect. Okay, and in this Ali's strong effect, apart from that, he gave many contributions. Ali's weak effect is there. Ali's multiplicative effect is there. Ali's additive effect is there. Okay, there are many effects given by Ali. I'm not touching about, but the concept, where we had a problem, from there we have to extend it. The concept is improving like that. And in the single species also, yes, the problems, yes, we are extending into harvesting model. In harvesting model is like, yes, we have Hyderabad city with the jobs, and somebody is getting, and yes, they are taking away from the jobs. Right now, in the present COVID situation, there is an option called work from home. So here, whatever the work or task is there in the Hyderabad city, and people are working from out. So ultimately, who are staying in are getting defeated, a problem here. So that harvesting models are also there. So those, of course, I'm not giving here, but the thing is in no future topic, yes, will be giving about it. So that harvesting, what will happen here? These resources in the growth, we are taking it minus H will be taking that harvesting to that, right? That will be touching, and the formulation will extend it and will give solution, conclusions, everything. Yes. And there are some other growth models also there. This Pavalla model is there, and Compage model is there, and one Battlefly model is there. Okay, there are various models are there depending on situation. So they modeled it, and of course they gone for their analysis. Yes. Now we have to look into the models called competitive models. Competitive models are basically sorry, there were soft animal, many animals are there. But the thing is, suppose if you take a goat, always there will be a competition between two. So here we'll be getting two type of species, right? Here in general, many patients, if you notice it, those will be affecting with only one kind of disease. Could you think about it? People will not get malaria and typhoid at a time. Those will be suffering with either malaria or typhoid, not both. In many cases, very few cases may be there. In such case, the dominance of both the species may be same. So in such cases, no patient will be getting affected with the same disease or more than one disease. But the thing is that the interspecies competition will be there. So that model we have to take into consideration, right? So that is giving negative feedback on the other. Suppose I'm taking somebody's. Here I gave logistic model for n of t. So the same model, if I'm taking it from there, if I'm taking on the depending on their food, so there will be definitely negative feedback on them. Means what? In whatever the food is available for them, I'm taking about, right? I'm not included in that. So in such case, no, their food level, their depreciation will come. So the net to negative feedback will be there in the growth of every species. Now, whenever we are taking competent species, more than one, so for each and every species, will be generating one logistic equation, and that logistic equation will be consisting of negative feedback by the some other. So the basic idea in the started with Lokta and Volterra, those gave a model, right? This Lokta is American mathematician, biologist actually. He gave a primary examples on plant population, okay, and their behaviors, animal dependent on the plant and food. This Volterra is Italian, right? And he retired from the pure mathematics, okay, in 1920. Yes. Now they gave this Lacto Volterra model. Yes. Can you hear me, sir?
Yes, yes. ఏమైంది?
Excuse me, sir. Kaladar, sir, your voice is not audible.
Dr. Kaladar, on your side there is a problem. Hello.
Yes, sir. Now is it audible, sir?
Yes, sir. Yes, sir.
Yes, visible. Okay. Now these Lotka-Volterra equations are a pair of a first
Screen
order
not sharing, sir.
equations. Not sharing.
You're using Google Meet or Zoom?
No. Microsoft.
Okay.
Now, sir,
No, sir.
Okay.
visible.
Yes, sir.
Visible.
Yes, sir. Visible.
Yes. Okay, thank you. Yeah. Now these Lotka-Volterra equations are simple pair of a first order non-linear differential equations only. Those describes the dynamics of biological systems in which two species interact. One species is acting on the other. One category of species acting on the other. Right. So this is the earliest pre-predator model based on these mathematical principles. And this forms on the basis of many models used today. Now whatever the models we are using, we are taking it as a base as this Lotka-Volterra model only. So here the basic principle is the population change in time, stuff going in, stuff going out only. With this concept only, these Lotka-Volterra had developed their model with the two species. Suppose if alpha is the rate of competition for common resources, alpha, right, that is imposed by the first species. Common resources, but imposed by the first species, right, on the second. Then there will be negative impact, that is minus alpha into n1 n2 term into the growth equation of the second species. If the first competitor is going on second is going on the first. So there is two impacts, negative impacts on two logical equations, right? Okay, those models, yes, we considered here. Now, if you neglect these two terms, if you neglect this alone term, right, the C1 into N1 into, if the term is not there, this is a simple single species model for N1. And similarly, if it is not there, this is a single species model for N2 alone, right? And because of these, right, interspecies competition, N2 entering into N1, N1 is entering into N2, right? So this is the two species logistic basic model. After that, no, with harvesting, so many models has been improved and developed in recent years. Here C1 and C2 both are constants, okay, and there is a competition, right? So N1 and N2 are there are various parameters, okay, involved in that. Yes. Now after the non-dimensionalization, so this model we are getting it, okay, dou u by dou n. This is for first species, this is for second species Q2. We are getting it, okay, and when we are getting it, we are going for this equilibrium points. Same story. So there was earlier there was only one function f of x. Now here it is like f of x comma y is equal to 0. We are solving for their roots. So when we are taking f of x comma y, first one, f of x comma y is equal to 0, u1 is equal to 0 will be getting, and 1 minus u1 minus a1 to u2 we are getting it. So we are taking 0 here, and with this the combination with the second species will be getting u1 is equal to 0 with u2 is equal to 0, 0, 0 and 0, and from this whatever the things we are getting it here, pairing we are doing from first and second species. Second case is we are taking this is 0, and with this we will incorporate it, and we'll be taking these two, right? So one pair will be taking, so totally 4 points will be getting it here. First one is 0, 0. If you take u1 is equal to 0 here, so u2 is 1, so that's what 0 comma 1 here. And the next one is u2 is 0. If you take it here, so u2 is 0, that is u1 is 1, so 1 comma 0. And the roots of these two will be getting 1 minus a12 by 1 minus a12. So this point will be getting as a fourth equilibrium point. But the thing is, ultimately one condition says that here our equilibrium point must be positive. So here, to become positive here, what are the possible combinations are there? So those will look into it. So this is equilibrium point here. So when we'll be getting here a12, a21. If both are positive, what will happen? A12 is positive, A2 is also positive, so both are positive, right? And sorry, I'm sorry, this is greater than 1. If both are greater than 1, so 1 minus greater than 1 is negative. So 1 minus greater than 1 is negative. Negative by negative is positive. This point is becoming positive. Similarly, this point also becoming positive when A12, A21 both are positives. Okay, in such case, the denominator is becoming negative, numerator is also becoming negative, negative by negative. In either case, yes, if those are less than 1, less than 1, this is positive, this is positive. Positive by positive is positive, and similarly, this point is also positive. So if you take a graphical representation for those two equations, right, these two equations, 1 minus u1 minus a1 to u2, and the second one, yes, you just see it, right? And about their roots, intersection points with the coordinate axis, we are taking u1 and u2, right? And first line 1 by a2, and the second line is a12. A12 is meant for the first equation. There is an intersection. So if there is an intersection, what does it indicates? That indicates that there is interspecies competition is there, right? If those are not joining, this fellow is different, that fellow is different. There is no interspecies competition. So this joining point is there, and that will happen only when these two conditions. And other cases also there. What about those we have to see? One is here, I considered both positive, both negative, but the thing is, one may be sorry, one both greater than 1 or both less than 1. But the thing is, one may be greater than 1 may be less than 1, and the other one may be greater than 1, this one may be less than 1. In such cases also, we have to see about them. So the first case I am analyzing it about both are negatives. In that case, if a12 is less than 1, so then 1 by a12 is greater than 1. So 1 by a12 is greater than 1. So that's what a12 is more than 1. Then
How the
a21 is
graphs?
yeah, graphs were drawn for those two equations. These two
Which
equations only. These two equations we have. Yes. 1 minus u1. Two equations we are getting from the two logistic equations. Could you see my slide, sir?
Yes, visible.
Yeah. 1 minus u1 minus a1 to this side. These two equations plot I have taken, right? So from there we are plotting by taking necessary conditions about a1 and a12 and a21. So those graphs are plotted here. So yes. Now when these both are less than 1, so we are getting this plot. Then there is an interspecies competition here. So a21 is more than 1. Here a21 is less than 1 means 1 by a21. When you are solving that equation about intersection points, we are getting 1 by a21. Here, if you see this, sorry, I could have added that slide. Yes, here you see here when to get the intersection point with u1, we are taking u2, u2 is equal to 0. So then we'll be getting u1 is equal to 1. So intersection points with the u2. So by taking u1 is equal to 0, we'll be getting u2 is equal to 1 by a12, right? So intersection points with the coordinate axis is simple logic, and we are taking it, right? And whether those are greater than 1 or less than 1, that we have to see here. So 1 by a12 is greater than 1, 1 by a21 is also greater than 1 with this condition actually. So here 1 by a12 is more than 1, 1 by a21 is also more than 1. So those are away from it. And this is the first equation with respect to u1. This is the second equation we plotted. So with the help of this, there we could see this intersection point. This intersection point reveals about that inter-species competition, whether there is a competition or not. Those are fighting. There is a common point. So that we are taking it. And the other one is a21 greater than 1, a1 both are greater than 1. We are considering it. So when a21 is greater than 1, 1 by a12 is less than 1. So you just see it is below 1. Similarly, a21 is greater than 1 means 1 by a21 is less than 1. So that's what before 1, a21 is 1 by a21 is there, 1 by a12 is there. So again, if you plot those two straight lines, again there is a common point, intersection point. It indicates that there is interspecies competition, right? And then the other case I told, right? There we considered both greater than 1, both less than 1. But the other possible combinations also we have to see. One is less than 1, one is greater than 1 are taken. So a12 less than 1 means 1 by a12 is greater than 1. So 1 by a12 is away from it. And the next one is a21 is greater than 1 means 1 by a21 is less than 1, which is below 1. So if you plot those two lines, you see, is there any connection? there is no interspecies competition because there is no joining point between them. Then no commonality is there between them. So similar case happened with A12 is greater than 1 and A21 is less than 1. So finally, about these 4 points, so what I mean to say is, when both are greater than 1, there is interspecies competition. A1 to A21, if you remember, those are giving a negative impact on the other species, right? Right. So A1 to N1 N2 is there, A21 N21 N21 N1 is there. So those are creating interspecies competition among N1 species logistic equation, N2 logistic equation. But at a certain range, certain values only, it is giving that competition among N1 and N2 species. So with this, yeah. With this, no, I would like to conclude about it. But the thing is, still further extension, I don't want to reveal it because that is another research problem, right? Which is not published under reviews. I cannot reveal it. So I'm stopping with this, right? If this again, still I'm giving idea how we are improving these equations. That is by introducing harvesting. Here harvesting is not there. Simply interspecies competition is there. Now I've taken 2 species model, but there are maybe more than 2 species also, right? Such cases, another equation will be adding to that logistic equation, another logistic equation, but with the interspecies competition. If there are 3 N1, N2, N3 will be they like alpha 1, A1, N1, N2, A1, N1, N3 in the first logistic equation. Second equation is B1, N2, N1, B2, N2, N3. Likewise, third equation will be consisting of, let us take C1, C1, N3, N1, N3, N2. So the competition will improve it, or will increase it, and it will increase the complexity of the problems. And see, with this, still after stability, here when your tissues, when one kind of tissues are going to be suppressed, the other kind of tissue is going to be dominated, right? Those things we can elaborate and we can go for analysis, right? And here about stability, still we can extend it this with the help of Jacobians also. After taking this, for these 2 equations, we'll be going for yes. Now with the help of G of U1, U2, we are going with Jacobian of this F and G with respect to U1 and U2. Then at the saddle points, these equilibrium points, yes, we can test its nature. So based on the eigenvalues of that, if all eigenvalues are negative, then that point is going to be stable point. Otherwise, it is going to be unstable point. So I'll conclude, right, all tissues, and of course may create phobia about it, how the spreading, and I will start with a simple table which was given by our stalwart, Professor Ramanujan, right? This is a simple magic square box given by Ramanujan. What is the special in it? Few people who are from mathematics background may know about it. You just take the column sum, any column sum, or you take any row sum, you take any diagonal sum.
Sum is the same.
Yeah, and some of the corner squares also you take it, and some of the sum is the same, that is 139. And if you see the first row, you could realize it. What is that? 22, 12, 18, 87. That is the date of birth of our stalwart Professor Ramanujan. Okay, and let me thank once again Chandrasekhar sir for giving me this opportunity to express my views. Thank you, sir.
Yeah, Dr. Kaladar, please share this presentation in the group so that we can read once again all the things. Yeah, your
Okay, sir. From
presentation.
Kala side, we'll see, sir.
Yeah.
Hello?
Okay.
Thank you, Dr. Kaladar, sir. Thank you for accepting invitation delivered up to participants. Thank you, Kaladar, sir, once again. Thanks to all participants. And thanks to our research person, Dr. Kaladar. Thank you very much.
Hello. Hello, sir.
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 Kaladar, sir. All participants.
Thank you, sir, for your excellent explanation, and thank you for giving your precious and valuable time, sir. And thank you, one and all, sir.
Thank you, sir.
Dr. Kaladar, I have a doubt. Hello.
Excuse me, sir.
Yeah.
Dr. Kaladar, sir. Maybe network problem, sir.
Hello. These questions are there or session is completed? Interaction session is there, is not there?
Some network problem. Some network
Hmm.
problem, maybe network problem with research person, sir. Just we'll wait for 1 minute, sir.
Okay. Because you want to interact with him.
Otherwise, I will share his mail ID, sir. In the group, you can interact with him, sir.
Okay. If it is possible, I will interact. Otherwise, you will share the information he presented and mail ID also.
Yes, sir. Now let us wait for 1 minute, sir. If he is there at the time.
Yeah, sure. Okay. Sure.
I think he's disconnected, sir. I'll share his mail ID, sir.
Okay. Mail ID and his presentation also keep in the group, sir, so that we can learn some new ideas.
I will ask him, sir. I will ask him presentation, sir. Sure, sir. Right.
Because
So
his presented, his presented model is applicable to this present COVID situation. How to control the growth rate also we can visualize.
Yes, sir.
I'm also from NIT Warangal, completed my PhD.
Right now, where
I'm a
are you, sir?
faculty at presently I'm working at Mathurst Engineering College.
Oh, Saidabad. Okay.
Yeah, Saidabad. My teacher was Dr. Pattabhiramacharyalu, who taught me about this mathematical modeling, and his scholar is my guide, Dr. N. Srinivasacharyalu. Under his supervision,
sir.
I completed my PhD.
Okay, sir. I'll share his mail ID through group. Okay, sir.
Yeah.
Thank you for participants. Please,
You are a mathematics faculty.
I belong to mechanical engineering, sir.
Acha. Who is mathematics faculty or active mathematics faculty?
Prasad Gattu is there. No, he is faculty of mathematics.
Okay, sir. Please, my request is try to share his presentation so we can learn new things.
I'll ask him presentation. We'll share by today evening. Okay, sir? Right.
Okay. Thank you, sir. Nice platform to learn new things. Thank you.
Thank you very much, sir. Thanks to all participants. Prasad, please close the session.
Thank you, sir. Thank you.
Yeah, we are signing off.
ఒక 4 రోజుల్లో నలుగురు ఈ 4 రోజులు నీ గురించి నాకు ఏ టెన్షన్ ఉన్నారంటే నువ్వు భాష 1 మంత్ ఇండియా పెట్టింది హ్యాపీగా హాలిడే ఎంజాయ్ చేసి అటు నలుగురు సెటిల్ అవుతాయి ఇండియా పబ్లిష్ పేరెంట్స్ ఇవాళ ఎంజాయ్ చేస్తే ప్రతి విషయానికి మూలాలు అక్కడ మొత్తం మోల్టెన్ చాక్లెట్ ఫ్రెంచ్ విషయంలో కేవలం 5 రూపాయలు.
అమ్మా నేను బయటకి ఎప్పుడు వెళ్ళచ్చు తెలియదమ్మా కానీ మనం ఇంకా సీట్గా బయటకు వెళ్ళాలంటే ఇంట్లోనే సీట్గా